Good morning, and welcome to this Conservation Applied Research and Development, or CARD, webinar on reconsidering cooling loads in Minnesota. Thanks so much for joining us today. I'm Mary Sue Lobenstein. I'm the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. And with me today is Adoy D, who is an energy planner principal at the Conservation Improvement Program Unit at the department. Adoy provides oversight and regulation for natural gas and electric utility energy efficiency programs as part of the implementation of Minnesota's Energy Efficiency Resource Standard. He has research experience in public policy design, computational modeling, and econometric analysis. Our presenter today is Ben Schoenbauer, a senior research engineer at the Center for Energy and Environment, where he conducts research on new and innovative technologies and ideas dealing with residential and commercial energy efficiency. His work includes identifying new opportunities, conducting field research, identifying and pursuing funding opportunities, and disseminating the results of research he's conducted. Ben's area of focus includes water heating performance, service water heating, and residential HVAC systems. Welcome, Ben, and thanks for the presentation today. Before we start, I'd like to go over a few webinar basics, most of which will be familiar to you. Attendees will be in listen-only mode. We'll answer questions at the end of the presentation, but as they occur to you, please type them into the Q&A box and send them to us under all panelists. We'll do our best to answer all questions within the time allocated, but if for some reason we don't get to all questions, we will answer them sometime after the webinar. This webinar is being recorded and will be available at a later date on the department's website, and the slide set from the webinar will also be available. By way of background, this webinar is one in an ongoing series that's designed to summarize results from research projects that are funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of that fund is to help Minnesota utilities achieve their energy savings goal. $2.6 million of the fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results of research programs and projects provide utilities with data to enhance their energy efficiency program designs within their SIP portfolio. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar addresses the residential sector, and will discuss the current state of cooling in Minnesota and opportunities for homeowners, contractors, and programs to increase the overall performance and energy efficiency of cooling systems. Now I'm going to turn it over to Ben for today's presentation.
Hi, thanks for the introduction, Mary Sue, and thanks everyone for tuning in and joining us today. On the screen now, you just see a brief agenda of today's presentations. We'll start with a discussion on why residential cooling loads are important in cold climates like ours. Then we'll talk generally about the loads in Minnesota, the cooling systems that are used to meet those loads, and then discuss some of the recent innovations to cooling systems nationally and opportunity for energy savings across the residential sector. Finally, we look at how those load systems innovations can be applied to Minnesota. And then we'll spend some time looking at a tool we've developed to assess the potential and then touch on key results. There are several reasons why we should care about cooling in Minnesota. The first is increasing applications. Air conditioning use is on the rise globally. The EPA, among others, contribute to increased installation of air conditioning and future increases in AC installations primarily due to economic development, both less expensive AC technology and expanding economies, bringing resources to more people who previously may not have had the ability to choose AC. Additionally, large-scale trends of populations are moving towards warmer climates with larger cooling loads, which will only increase installations. Nationally, these trends are also on the rise for similar reasons. Less expensive systems are becoming more available, and urban populations and heat islands are rising. In Minnesota, in the past, AC was rarely considered, but as of 2015, about 75% of homes have AC systems. Central AC systems are now the standard in new homes across the state, and air conditioning is becoming the norm. Another reason air conditioning is important is that we know that AC loads are a significant contributor to peak electrical loads. Most Minnesota utilities are still summer peaking. Those summer peaks typically occur on the warmest days at times when daily temperatures are at a maximum and house load occupancy schedules overlap, creating a large afternoon use period in most typical homes, as we can see in this chart. There is, however, a big opportunity for efficiency, and that's why another reason why we should definitely continue to consider cooling loads in our climate. In 2018, CE completed a DER-funded electrical savings potential study for the state of Minnesota. As part of that work, distributor sales data was obtained for HVAC equipment across the state. This chart shows the distribution of efficiency ratings for the 100,000 air conditioning systems sold per year in Minnesota. As we can see, the vast majority of these systems are sold at the SEER 13 level. That's the minimum efficiency rating allowed to be sold by the federal government. Over 60% of the units sold in the state are minimum efficiency. Additionally, only a very small fraction of the market is the highest tier efficiency ratings above SEER 18. This shows the vast opportunity to move from the minimum efficiency equipment to higher tiers of efficiency. This chart also breaks out sales by region, and as you'd expect, colder regions with smaller heating loads have a lower penetration of high efficiency equipment. Now we can move on to a little bit of background and general discussion about cooling loads in the state. So first, just want to touch a bit on the anatomy of cooling load and how we can think of the sources for the need of cooling in residential homes. We can break the cooling load into a few categories. First, loads can either be external or internal. External loads come from outside the home and include heat transfer through the envelope, infiltration, solar radiation. Internal loads come from people, operation, lights, equipment, and other appliances and other things inside the home. We can also break out the loads by sensible and latent heat. Sensible loads refer to the dry bulb temperature and is the amount of heat that must be removed from the air inside the home in order to maintain a certain temperature. Latent loads refer to the wet bulb temperature and is the amount of energy required to dehumidify air inside the home. Location and climate obviously have a significant impact on the cooling load of residential homes. This plot shows the scale of impact around the state. The numbers on the chart are the cooling degree days measured for a typical year in various Minnesota locations. Cooling degree days are the annual summation of the difference in the daily average temperature and a base temperature, in this case 65 degrees. They're a representative measure of how significant the cooling load is for various locations. We can see from this figure that cities in northern Minnesota have about half the cooling load as cities in southern locations. And we can also see the significant heat island effect in the Twin Cities area. Because cooling loads are much smaller than heating loads in cold climates, like Minnesota's, because cooling loads are much smaller than heating loads in cold climates, there have not been as many resources spent to understand the full picture of cooling loads in the state. There is some field data, but it is limited. We do have several sources of information that we can use to estimate cooling loads across the state. There are measures like the Minnesota Technical Reference Manual that compute loads based on equipment capacity and equivalent operating hours and use calculation to determine estimate annual loads. The first table shows the cooling loads based on this methodology for several regions in the state and several size pieces of equipment. We can see these loads range from about 500 to 2,000 kilowatt hours per year. The second table modifies those estimates based on field data collected as part of a previous CARD research project looking at improving quality installation and maintenance practices for HVAC systems in Minnesota. This project measured actual performance from a large number of HVAC systems in the state. And we can see that using that data, the actual usage has been reduced about 25 to 40% over the estimated usage using the TRM methodology. That reduces us to a range of about 350 to 1,300 kilowatt hours per year. We also have some additional data points around the average annual loads for the state. The Residential Energy Consumption Survey data and the Minnesota load profiles as part of the TRM both show annual loads around 600 kilowatt hours per year, which align pretty closely with that field data we just discussed. Next, we'll move on to the cooling system types. I won't spend too much time here, but there's plenty more background information in the report. I just want to briefly mention the systems that we covered. The project generally considers as many system types as possible around AC systems analysis, but wanted to highlight the most significant systems we thought of. The first thing that comes to mind when someone says air conditioning is a split system central air conditioner. This is the standard whole house air conditioning system that is available in a wide range of efficiency levels, savings, and with a lot of different features. It also has a similar product in the centrally ducted air source heat pump. The air source heat pump is very similar in performance on the cooling side, but also has added abilities to provide heat to a home. Another type of cooling system we considered that has increasing use is a mini-split or ductless system. These systems are typically smaller than the central systems and are designed to provide cooling through an indoor head as opposed to through a ductwork system. They're typically applied where there is no ductwork or the ductwork is limited in a specific zone of the house. For example, homes with hydronic heat or a new addition where adding ductwork was difficult. They are also comparable to ductless heat pumps, which are also available in the market. We also looked at room air conditioners, both window style and portable in-room units. These systems are typically lower first cost alternatives to the more significant systems we see here, and they're also tend to be less efficient, but do have some useful applications that address specific needs inside a home. So now I'm going to move on to the opportunities for savings in energy use. Air conditioning equipment manufacturers, as is the case with most HVAC industries, have responded to continued interest and need for higher performance equipment with lower energy use. Air conditioning systems continue to be developed and come to market with higher efficiency ratings. New systems are being introduced every year with higher SEER ratings. Currently, there are systems on the market with efficiencies that are 2 times that of the minimum federal allowable efficiency. Continued improvement of systems has also resulted in lower cost equipment at the mid-tier and lower tier efficiency and performance levels. Another area of continued growth in these is the features that these systems have. One example is variable capacity performance. Systems with variable capacity are operating at multiple stages or multiple speeds, as opposed to a single capacity, single speed system as is traditional. The plot on the lower left demonstrates the benefits of variable capacity. The plot shows the outdoor air temperature along the x-axis and the cooling capacity along the y-axis. The blue line shows the load of the home. That load increases as outdoor air temperature gets hotter. The red line shows the delivered capacity of the single stage system, which is relatively constant around 30,000 BTUs per hour. The black and gray areas show the available capacity ranges of a variable capacity system. When it is nearly 90 degrees outside, the house load, the single stage capacity, and the maximum capacity of the variable capacity system are all about the same. And under these conditions, the two systems would operate in a very similar manner. But in the upper 70s or low 80s outside, the house only needs about 5,000 to 10,000 BTUs of cooling. The single stage system will still deliver around 30,000 BTU per hour in these conditions, resulting in the system cycling on and off fairly rapidly. The variable capacity system can reduce its capacity to deliver about 12,000 BTU per hour, resulting in a much more continuous operation and having a significant benefit to the overall efficiency and comfort of the system. It does turn out that the SEER rating does a fairly good job of accounting for benefits like variable capacity. These advanced features like variable capacity tend to be available on the higher end equipment, which also tends to have a higher SEER rating. The plot on the right shows that as we increase in level of modulation from the single stage on the right-hand side to the fully modulating system on the left-hand side of the chart, we can also see that the typical SEER rating of those systems grows from down near the minimum efficiency with the single stage to up into the SEER 24 to SEER 26 range for the full modulating systems. Another area of innovation and advancement is in controls. We've seen an increased push from air conditioning manufacturers to develop their own smart communication thermostats, as well as incorporating the ability to utilize third-party thermostats. Historically, programmable thermostat research has suggested that savings from these devices can diminish over time. Communicating and smart features provide a pathway to ensure that these savings are delivered in practice. We've also seen developing controls approaches to directly address user comfort. These controls may improve energy performance as well as comfort. One example is a dry, cool, or humidity control modes that address latent load and dehumidification in a home. Humidity is not directly addressed by the normal thermostat dry bulb temperature control mode, but does have a significant impact on occupant comfort. The latent load has increased importance in lower load homes where air conditioner runtime is often reduced and the internal loads, which are often higher in humidity, become a larger and larger part of the total load. Variable capacity systems can increase runtime and improve the ratio between sensible and latent cooling. Utilizing variable capacity and dry cool modes attempt to directly address comfort needs by controlling system runtime or directly measuring the humidity level in the occupied space, as opposed to using a dry bulb temperature approach. Another opportunity to improve cooling performance is in the operation and behavior of the occupants that use the system. This can be broken down into how the system is operated and how the set points are used. Research in warmer climates has defined 4 user types for air conditioning systems. The always or nearly always off homes for users that use their systems only a few days a year in the most extreme heating or cooling conditions. Set it and forget it homes for users who turn their systems on for the year, select the temperature, and then leave the temperature setting relatively constant for the entire season. Homes with a daily schedule for users that have either a programmable thermostat or manually use set points to maintain a relatively repeatable schedule. And then manually switched homes for users that exhibit more on-off type behavior. These homes you can think of as people that sort of use their thermostats more like a light switch in terms of controlling their device. In addition to the operational modes, we also can have a big impact on behavioral performance and energy use around what the actual set points are used. This is both the temperature set point that occupants feel while they're occupying the space, but also the setback that they're willing to use during unoccupied times. The final area I'd like to discuss in this category is applications. Traditional quality installation programs have done a good job of ensuring proper sizing and good charge for these systems, for traditional systems, but these programs will need to continue to evolve as cooling applications and controls change and grow. One application that is shown to promise is the zoned approach. This approach involves installing a smaller high-efficiency system in a high-load portion of the home. A small Florida pilot found that 33% reduction in cooling energy using the zoned approach. But those savings are very occupant behavior dependent. Another application worth considering is combined heating and cooling. Air source heat pumps have been a big area of research for many, including CEE. The significant improvements to the heating applications of these technologies have made them a big opportunity for efficiency. Air source heat pumps have the same ability to provide high efficiency cooling as high SEER central AC systems, with an incremental cost between heat pumps and central air AC systems that's very similar when looking at systems with similar specifications. But air source heat pumps have the additional savings potential in the shoulder heating systems where air source heat pump efficiency can be as much as 5 times greater than a traditional heating system. And for homes with electrical or propane heating systems, there are heating benefits over the vast majority of the heating season. So I'm going to spend a little time talking about barriers. By far the biggest barrier to high efficiency cooling to date is first cost. High efficiency systems are expensive and have limited penetration. This table shows some national first cost data from the NREL Residential Efficiency Measures database for the central split system air conditioning systems. These costs are likely lower than costs that we might get quoted by individual local contractors, especially at the higher efficiency tiers where local contractors have a very limited number of installs and experience with these systems. Cooling loads are relatively small and inexpensive in Minnesota. Energy use ranges from 500 to 1,500 kilowatt hours for central systems across the state. If we assume a 30% savings, that's anywhere from $16 to $50 per year at 11 cents per kilowatt hour. Even using that high level of savings, that would be about a 10-year payback for most cases. Beyond cost, there's a few other barriers that are worth highlighting. Availability is a barrier. Contractors don't try to sell these systems, and homeowners don't ask. As we discussed earlier, about 70% of the systems being sold in the state are of the minimum efficiency level, and the remaining systems are mostly in the mid range, SEER 14 through 16. Quality installation, as we mentioned, is very effective for getting good installation with current split systems. But as more advanced features like zoning, controls, humidity, and different system types such as mini splits are added to the market, quality installation programs will need to change and evolve to meet those needs. Rebate programs and approaches are changing for cooling systems. Even over the last few years, some Minnesota utilities have dropped or reduced air conditioning rebate levels. Others have increased air source heat pump rebate amounts. In some cases, this shifts the preferred system for contractors due to first costs. We have anecdotal evidence that more than one contractor in the state has chosen to install air source heat pump systems instead of central AC systems because the air source heat pump system had a lower first cost after applying rebates for a local utility. These applications aren't even considering using the heating capabilities of the heat pump. They've just chosen the system mainly out of that lower first cost. Well, this isn't necessarily a barrier, as heat pumps can have very high and very good performing cooling systems. It's a change to how we think about cooling and presents a barrier for implementing these types of programs. Savings metrics can also be an area worth considering. The SEER rating covers a lot and does a good job of distinguishing equipment, but as equipment continues to become more complex and applications increase in difficulty, it becomes harder and harder to capture true field performance with lab tests and efficiency ratings. At Minnesota load levels, this hasn't become a huge problem yet, but calculations methods can also play into this. Current TRM methodologies likely overpredicts actual use. If those actual usage levels are reduced, cooling rebates may be more difficult to justify with traditional methods. There are opportunities for additional savings from new applications, controls, and behavior, but they'll require new metrics or new calculations methods to accurately capture those savings. Having discussed those opportunities and advancements, let's look at how they apply and assess some Minnesota homes. So if we think about calculating performance, there's a large list of inputs that go into assessing the savings potential of these various options for cooling systems. These major characteristics include the house characteristics, which include size, envelopes, and weather data. As we can see in the figure, we've broken the state up into a few different regions to categorize the weather piece. Cooling system type, systems operation, occupant comfort criteria, occupant behavior. And when we take all those things in and we consider it, it's a huge number of combinations and lots of options to look at with all these variables. So in order to assess all these various impacts and opportunities for air conditioning, we've built an Excel tool that I'd like to do a brief demo of. Here's the tool. As you can see, it's an Excel spreadsheet. This tool is a set of engineering calculations based on a typical meteorological year data and a bin hour analysis. This isn't meant to be a full-scale building energy simulation, but instead a calculator to help measure the potential impact in priority areas for work for efficiency in residential cooling. We can see on the upper left-hand side of the tool a series of inputs. These inputs define the different use cases for calculation. The first group of inputs relates to the house characteristics and the cooling load. These include location, where we can see a drop-down menu. We also have house size and type and insulation level. The next set of inputs is around the application. These include choices about the number of zones and how those zones are defined in the home. The next batch of inputs is for behavior. First controls how the system is operated. We have choices for nearly always off, fixed, constant set point, or manually on-off behavior. The next choice lets you choose the level of set point for various temperatures at the thermostat. Finally, we can see an area where we're able to choose the type of system. We have choices for baseline, window units, and then tier 1 through tier 4 to choose an increasing level of efficiency for a central cooling system. On the right-hand side of this screen, we can see 3 charts. These charts are used to show the performance of the inputs selected and how the cooling load differs for this use case. We can see that this breaks up the cooling load by the different zones selected. We can see it also shows us the system performance for the selected systems. And in the third chart, we can see the total load of the use case. We can also see that this is compared to several different use cases around the state, and changing some of our house characteristics and other inputs will change that use and load, cooling load. And we can see the current case is highlighted in the yellow bar. In addition to the inputs, we also have a range of outputs shown here for the use case input. This includes the annual load, the annual use, energy use, some first cost information, and some annual operating costs. Once we've input all of our desired inputs, we can look at those outputs, and then we can move to the Runs tab. On this tab, we can see the current set of inputs and outputs in the first row, and we compare those to some historical saved runs in the tool. You can see there are a handful that we've run in this iteration. We can also see at the bottom here a chart that shows the overall annual usage of the current run compared to several of these historical runs. So we've been talking about this fully flexible mode where we can make lots of choices around a range of input, around the range of inputs. But we also have an option to evaluate some preloaded scenarios through this Scenarios tab. These relate to some of the choices and energy efficiency options that we've been discussing. We're currently looking at the baseline system, but we can alternate through a zoned application. You can see here now we've switched to having 3 different zones. And then we can also look at, for example, a higher efficiency tiered solution, which is shown on the screen now. So now that we've walked through a little demo of the tool, we'll spend a little time talking about some of the examples and highlights of running results in that tool. There will be more information, examples and highlights in the final paper, but I wanted to share a few today. The first area we examined with the tool was the efficiency paybacks of higher SEER equipment. This slide shows the results from running a scenario where a central air conditioning system was replaced with increasingly higher tiered solutions with increasing SEER for each choice. Each set of colors in this symbol represents an application with this series of increasing SEER systems. Increasing on the y-axis means that the system has increased simple payback. Moving to the right on the x-axis shows increasing cooling load. So if we take an example of a large metro area home with poor insulation or thermal properties, as we can see with the blue triangles. In this example, when comparing to a baseline minimum efficiency system, we can see that the options for the SEER 16 and SEER 18 solutions have simple paybacks of less than 5 years. As we move to the higher tier systems, SEER 20 and SEER 24, those simple paybacks increase due to the higher first costs of those systems. This chart shows that there are several cases where the cooling load is large enough to support high SEER applications that still have good paybacks. But as we move to systems with lower loads, that isn't always the case. Another example is from a set of options run through the cooling calculator were opportunities for zoned application. In this example, we're looking at results from a home without a central system that is considering adding cooling. The first row shows the base case using only a window AC in the master suite. It then compares to a whole house application using higher efficiency systems and in the more important zones and less efficiency or no cooling in the lower use zones. This table highlights on the subsequent runs that these options of zoned approaches can provide lower annual operational costs and or lower first costs. So as we conclude some of the high-level summaries from the tool, I should also say that as part of the final report, this tool will be made available for people looking to run their own scenarios and their own set of considerations through the tool. After having run a large number of applications and conducting the research for this project, developing the tool, and then using the tool to evaluate a large number of iterations of inputs, we have a few recommendations that we think should be considered for achieving cooling savings across the state. The first area of recommendations is to consider savings methodology that allow more flexible approaches beyond simple SEER improvements. This will help address some of the additional opportunities discussed today. This could be through a more complex tool like the one we've demoed, or through direct measurement or some other sort of program structure. The second area to consider is how addressing combined systems and applications can benefit cooling opportunities. We've briefly discussed the potential of air source heat pumps to provide both heating and cooling savings, but there are additional combinations such as cooling and dehumidification or reduction of the overall heating loads to improve envelope performance. These opportunities are not without challenge, but have potential to overcome some of the barriers for high efficiency cooling. So I wanted to leave you with some high-level results that we found from this project. Cooling installations in Minnesota, in the region, and in the nation are growing. Individual system loads are small, and traditional efficiency opportunities, such as increasing SEER, often have long paybacks. Occupant behavior and system operation have a large impact on energy use. Individual installs have low loads and can have high first costs for high efficiency systems, but due to the large number of installs, aggregate impacts have a huge impact on energy use and demand. There are lots of opportunities to reduce loads and energy use, but they require more specific applications-based approaches. Additional work is needed to outline best practices and program guidelines. Examples for additional work include further characterization of actual use and system performance data, evaluations of new opportunities such as combined applications, dry-cool modes, zoned approaches, and several others, considering ways to promote thinking beyond just the first cost, and market-based approaches to reduce those first costs. And with that kind of completes the prepared remarks. As I mentioned, a final report that has more detail on lots of these areas, and the tool will be made available in the future. And I think we have some time for some questions.
Yes. Thank you very much, Ben. Thanks for that presentation. And if you have not already done so, please type any questions you have into the Q&A panel and send them to us so we can ask them of Ben. Adoy, do you have questions for Ben at this point?
Thank you, Ben, for that presentation. It was really insightful. As we wait for questions to arrive, I had a couple of questions that we could probably get started with. The first question I had was, what kind of insights do you have related to how energy use varies based on the operation and behavior categories you identified during your presentation on the 23rd slide?
Yeah, so there has been quite a bit of research done on how these different usage types and operation impact savings in general and total cooling load. So we did define sort of the 4 types. Some of these types have pretty obvious impacts on usage. So for example, the always off or nearly always off homes, they're obviously going to have much lower usage because the systems just aren't run that much. Other types, the usage types can have a varying degree, of impact. So obviously programmable thermostats have been shown to save energy when used, but that can depend on what the set points you've used. The approach we've taken with the calculator tool is to give you some options, both for kind of setting up that structure for how the system is operated, and then varying kind of the degree to which those different operation modes are done through the thermostat set point control option. And so we've set those choices up to kind of represent the range of impact those systems can have based on some of the research that we've seen elsewhere, and then applied it to Minnesota's climate.
Thanks for that. That was really helpful. And then another question I had was, who do you think will find the tool you developed most helpful and useful for what purposes?
Yeah, so currently, as I mentioned, the tool is really built to look at as ways to evaluate sort of the range of impacts that these different choices can have. It's not really intended to show the exact savings in a specific house or kind of calculate the deemed savings for a whole range of applications, though it could be tweaked slightly to do those things. But really what we're looking at trying to do is to provide some ability to see sort of, does this idea, does the zoned approach, does it make sense to target this type of approach for a certain category of population? So we really see this being useful for people that are looking to sort of design areas for additional impact, or to see, is it worth looking at building a program out to target this type of technology?
Thank you, Ben. We received one additional question. Can you talk more about the strategy of a window unit plus a high efficiency unit in another part of the home, and if you see them being adopted?
Yeah, so this is a strategy. It's pretty new. There's been some research done on it relatively recently. As I mentioned, there's been a pilot study done in Florida. And really the idea is to look at in a house, if you have, depending on how the house is set up, you might have an area, especially if the floor plan is more open, where you have like a living room or a kitchen that has a vast majority of the cooling load. And so you can really address the cooling load in that area with a system like a mini split. And so there is significant value, if you're looking to add cooling, to maybe just adding cooling in a higher use zone. But there's also potential if you have an existing system to sort of enhance the performance by targeting a higher use zone. This can have a pretty big impact on the first cost of the system, especially as the mini split approaches come down. We can also combine this approach with with air source heat pumps and ductless mini splits to add some of that combined system performance as well. So it's an idea that's starting to take root in the higher usage areas, and we see some potential for it sort of in cold climates as well.
Thank you. Another question we have from Anne Craft is where she says, I've heard that you can't equate SEER between technologies. Example, comparing a 16 SEER traditional split system to a 20 SEER mini split. Is this an apples to apple comparison?
Yeah, that is a great question, and we do get into this discussion a little more detail in the white paper. And we touched on some of the barriers around the metrics and the ratings. And really, that's a great point, is that the SEER is really a measure of efficiency of the system, and does not really equate or address any of the differences in application. And so you can compare those two applications, a traditional split system to a mini split, in terms of their overall efficiency, but the SEER rating doesn't impact sort of how much of the application you're addressing, or any sort of outside system characteristics like duct losses if you have long duct runs or something like that. And so you can use it to some degrees to kind of compare efficiencies, but it definitely a perfect apples to apples comparison for trying to estimate energy use across a range of applications. That's part of the reason why we looked at this sort of tool approach, is so that we could kind of try to use some of the efficiency ratings metrics and combine them with some of the other applications variables to get a more accurate comparison.
Thank you. Another question we have is, if you were to choose a Minnesota customer at random, would you tell that person to keep SEER rating in mind or consider zoning or controls? I realize that there are many variables, but just curious whether on average one showed more savings versus the other.
Yeah, so I think one thing I guess I didn't address directly, but needs to be taken into account here is sort of, especially when you're thinking about a kind of specific implication, is how available or how practical some of these choices are. So, going for a higher SEER piece of equipment is always going to improve your efficiency. But doing something like a targeted behavior program, if you have a homeowner that's really on board and willing to try things and has some, willingness to implement a behavior program, you can see, much bigger effects from the behavior change than from an efficiency change. But if the homeowner wants it to be, 72 in their house all summer long, a behavior program probably isn't going to have as much impact. So I guess in general, I think, the range of behaviors we see from actual homes has the biggest potential to reduce the load, but how much movement you can get from a behavior program in any given house is widely variable.
Thank you. Two questions from Dan, maybe outside the scope of the project, but do you have any insight on relative benefits of efficiency upgrades versus demand response programs like cycling equipment as utilities request? And then he had another question. Do you think some of the benefits of zoning can be accomplished through vent closure in low priority spaces?
Sure. So to address the first question in terms of the relative benefits of efficiency upgrades versus demand response programs, so I think there are benefits and trade-offs to both, and I guess which are more important depend on, I guess, the goals of the programs or the needs of the utility. So general efficiency upgrades have the benefit of reducing the total energy use and, reducing the usage at any given time. A more efficient system, can meet that peak design load using less energy than a more inefficient system. But, those obviously come at a higher first cost. Demand response programs can be pretty cheap to cycle equipment on off, but they don't deliver you the overall, efficiency savings. So I guess it's kind of hard to say how which of those is preferable kind of broadly, but that really depends on a kind of cycle or a utility to utility or program to program basis. I guess in terms of, and then to the second question, benefits of zoning. So there have been a lot of different applications of vent closure ideas, either through just closing the existing vents you have in your home or adding smart vents to spaces. I definitely think there is some benefits there too, and that's another version of zoning that is worth considering. One concern I know that can arise with some of those vent closure systems is that if your central system wasn't designed with that intent in mind, changing the airflow by closing a large number of vents can have some impact on your central system performance. So definitely from design, vent closure and zoning in that way can be a big benefit, but you need to be careful when applying that to sort of any system where you don't know what the details of the existing central system.
Thank you. And then another question from Chris related to zoning. He says, can you talk about incremental cost of zoning in retrofit application? What all is involved in terms of labor and materials?
Yeah, so this can be, so there are several ways to approach this and, different system types that can be used for zoning. If we're talking about doing an independent new system, especially if we're trying to increase the efficiency of that zone, we're likely looking at a ductless air conditioner or a heat pump. Those, systems, it's much like your central system. They have an outdoor unit that's very similar, and then you have the indoor head that's mounted on a wall. Pretty common to see those as a ductless heat pump type install. The install cost can be widely variable depending on application and familiarity of contractors. We've seen them as low as a few $1,000s for a system, but as high as $6,000 or $7,000. So it's probably not an approach that we could say everyone go out and get ductless mini split, ductless heat pumps or air conditioners tomorrow. They'll be cost effective. But as that technology continues to advance and grow, I think it'll be more and more cost effective.
Thank you. Another question from Kevin: who is the intended audience for the use of the calculator?
Yeah, as I mentioned, I think right now, as it states, it's really around those looking to sort of make decisions about how to target resources and target programs that want to identify where to set up and prioritize for cooling savings. So it's maybe less of a contractor tool, homeowner tool, and more of a program administrator or a researcher. Those that are looking to kind of set some of this future work up and program work up. As we mentioned, I think there are applications or modifications that we could do to the tool in the future to make it useful for more users, if that was of interest.
Thank you. And then there's another question from Kevin. It says, the presentation indicates very small incremental cost of heat pump over AC. Is the better approach to move towards heat pumps since Minnesota is heating dominated? And if so, what might be the potential payback scenarios for a homeowner looking at heating and cooling?
Yeah, so I think there are several, I guess I'll give some high level comments, but I guess in general, I'll say there's quite a bit of work going on heat pumps. So I don't want to get too far into the details. I think there's other card projects and other card projects that CE is working on that can try to address some of these things more broadly. But I do think, so I say the cost difference is minimal. The caveat I put on that, and then I'll highlight again, is that we are talking about systems that have similar ratings. So a high efficiency air conditioner is only or a high efficiency heat pump is only a little bit more expensive than a high efficiency air conditioner. The pieces, the components to that equipment are relatively similar. There's only a couple of small differences. You can, obviously there's a range of efficiencies and performance across both technologies. So you got to compare similar equipment. That's for the equipment costs. The installs are very similar. There isn't really much difference, but there is a lot to do with sort of contractor familiarity in those pieces. So sometimes while the costs should be pretty similar, depending on who you're working with, they can be in practice quite a bit different. So that's another thing to just throw out there. I do think, it really does depend on, what your motivations are and what your existing system is. Are you using natural gas? Are you using electric heat? Are you using propane heat? Where the advantages and disadvantages are for, trying to heat more and more with your heat pump. So there's a lot of additional inputs to think around that, but I definitely think there are a lot of applications where heat pumps, make sense to give you some heating benefit and a lot of cooling benefit over traditional systems.
Thanks, Ben. I don't see any additional question. There's one comment from John. He says, nice work. I have researched this information on my own in order to build an energy efficient home in Steams County. A big help there is the rebates and the off-peak electric rates offered. Thanks to your work, I was able to determine that a cold climate air source heat pump was the best.
Yeah, I think that's That's great feedback, and I appreciate that. And I think I think that it's a good point that kind of the rate structure and the rebates can vary, depending on where you're located, but it can be a pretty significant benefit for both cooling only equipment and for air source heat pump equipment. So definitely important to consider.
Yeah, absolutely. We currently don't have any additional questions.
Great. Thank you. Thank you, Adoy, for managing those questions, and thank you, Ben, for answering them so adroitly. And if you have any follow-up questions about this card project, please feel free to contact one of us. In the meantime, I'll just point out that the recording of this webinar and the slide set should be available on the department's website, and the final paper will be available in a couple of months. The recording and stuff will be available probably by the end of the year. When available, you can link to either of these from the quick links on our Applied Research and Development webpage as indicated on this slide. This R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the address at the bottom of this slide. And before you go, I want to thank you for participation today, and we really appreciate your interest in CARD projects. And before you leave, I want to take the opportunity to mention two more upcoming one in December and one in January webinars. On December 10th, the Center for Energy and Environment will be back to present data they gathered about a medium and large commercial and industrial refrigeration market study they did in Minnesota. And then on the 21st of January, 2050 partners will discuss the results from an 18-month process to develop a roadmap for a Minnesota Codes and Standards program. You can keep abreast of upcoming webinars and other news related to the Minnesota Conservation Improvement Program by signing up for the SIP updates on our email list. You can use the link on this page to sign up for it. To do that, in the meantime, contact me if you have questions or suggestions. And I also want to point out as a reminder that there'll be a short evaluation that launches after the webinar. Please take a few minutes to fill it out so you can let us know how we did today. Thanks again, and have a good rest of your day.